Hello, everyone, and I would like to welcome you to my project on Programmable Logic Controllers. My name is Michelle Larsosa, and I am currently a student in the winter 2022 semester of ECE 560. And I will go ahead and get started with my presentation. So programmable logic controllers, they're also known as PLCs. So I will be using that reference mostly throughout this presentation. And PLCs are able to receive data through inputs and send operating instructions to outputs. The controls for the system's functions are used by PLCs using the internal logic programmed into it. The history of PLCs were first developed in 1968 by engineers at General Motors. And the purpose of them developing this type of controller was to help control and automate the manufacturing processes in the auto factories. So as our country had moved into the industrial age, there were conveyors being used and a lot of people needed to help build automobiles. And so the onset of PLCs helped to streamline that process more efficiently with the use of the computer, basically, as opposed to using so many people. The systems were able to run and maintain themselves, which also helped with cost and efficiency in the auto plants. And in continuing with the history, the initial elements that were used to make up the construction of the PLC were solid state components that were modular and expandable, that contained 16 units that could be expanded to 256 and 16 outputs that could be expanded to 128. It offered easy programming and reprogramming, and it was able to also store programs during power outages. And so the PLCs of today are able to build upon these initial specifications. So the use of the PLCs that I was studying for my research are closed loop systems. Open loop systems can also be implemented for PLCs, but for the purposes of auto factories and for systems that are supposed to be able to maintain themselves on an ongoing basis, those would be more closed loop systems. So other examples would be like the traffic light, central air conditioning, things like that that are able to run around the clock with minimal supervision, or basically non-manual activity. These systems should be able to run by themselves. Examples of open loop systems would be like a hair dryer. Things that you can start and stop. If you pick up a hair dryer, you turn it on, you use it. The controller inside of that hair dryer is supposed to help with its stability and efficiency. But when you're done with it, you can turn it off and put it away. Whereas with a closed loop system, you want to be able to have that, run continuous cycles with some supervision, but mostly those systems should be able to run and operate by themselves. So with closed loop systems, the advantages are high accuracy due to its measurability. So its outputs can be measured, and there you have more stability and efficiency. The idea is to have, if needed, to have people on standby, for maintenance, in emergency situations, because sometimes there are things that will happen, beyond, the system's control, or someone would need to go in and, fix a part, or if a fuse shorted, you would have someone go in and tend to the system if there's actual downtime. But again, the idea is for that system to be highly stable and efficient for it to run continually by itself. And the disadvantages for closed loop systems, there's not that many, but the initial cost of implementing a closed loop system is high. It could be in the tens of thousands, if not hundreds of thousands of dollars, because the idea is to have the system so strong and so stable that you want to make sure you have all of the parts that are required and necessary to go in, and to have the right people to help install and to further monitor and service the system as necessary. The other, again, going into the other disadvantage is ongoing and around the clock maintenance. So having people there to help service the system when needed, those people have to be paid for their service in monitoring the system. So mostly cost, high cost is really like the main disadvantage when it comes to closed loop systems. So there are, the main core components within a PLC, and those would be the power supply, the input module and output module. Sometimes you might see it combined as the input and output module, but the input has a function, and then the output has a function as well. And then you have the central processing unit, or the CPU, and the memory. So the power supply, as the name states, it provides power to the PLC. It helps to energize it, it gives it the power so that it can run and function. It then also converts the input source power into the signal level voltage by using the processor and other modules. So it gives power to all of the modules combined for them to work properly and in session with each other. The power supply can also come in different sizes and power ratings depending on the type of PLC that's being used. And so those are the types of things that, the engineers who are planning and designing the system need to look at when implementing this type of system. The common output voltage is 24 volts DC, and the common current ratings are 2 to 10 amps for smaller systems and up to 50 amps for larger systems. The input module. The input module detects the status of input signals. That would be the push buttons, the switches, temperature sensors, and limit switches. The input module also receives signals from switches and sensors and sends them back to the processor. So there's ongoing communication between the input module and the CPU. Also, the input module can either be discrete or analogous or continuous. So it's able to be one or the other, or they can also be converted back and forth with the use of the programming that's set up for the system. Output modules. The output module control devices consist of relays, motor starters, and lights. So again, for something like the traffic lights, we see red, yellow, green. Those are the output modules. So all of the controls that are inside of that system are able to then produce and decide whether the light is going to turn red, yellow, or green, or rather green, yellow, and red. So the same in an auto factory, the output module helps to determine how the system's going to run. Is it actually going to run a full cycle of parts, or does the that particular cell or line doesn't need to be stopped for a certain period of time? Usually at the end of the day, at the end of a work day or the end of a shift, the system is down, but there's still a lot of times is some power still being provided to that cell for it to be able to function when it's time to function. So there's not like a hard or cold startup. The output module is also divided into 3 different types. Based on the output, you have the relay, transistor, and triac outputs. With the triac, it is capable of controlling the AC loads, where the transistor output modules only control DC loads. And so basically the triac output is dependent upon however the transistor output is designed, or however that's being used within a particular module. Then the relay is pretty self-explanatory. It's best suited for both AC and DC output devices, and relays are used quite a bit throughout PLCs, and you'll see them a lot in the setup of ladder logic, or the programming logic, which we will see later on in this presentation. So the central processing unit in memory, this is kind of like the brain and the heart of the system. The CPU is pretty much is the computer. It's the smaller computer that then can communicate with other computers for the devices that are attached to it. The CPU runs the programming language. In this case, ladder logic is used a lot throughout PLCs. The CPU runs ladder logic routines that help to automate the factory processes. It also processes data and computations by accepting inputs and then producing the appropriate outputs. For the memory, both ROM and RAM memories are used. So the ROM contains information and memory for the operating system, the driver, and application programs. And the RAM stores user-written programs and working data. So the RAM basically is storing like the information that's like working data that can be updated and changed, relatively, throughout the course of a shift. So for example, for the engineers that are monitoring a system that's running in the factory, the engineers may have to make adjustments to the programs depending on how that particular line or cell is being ran. If there are adjustments that need to be done for the sake of efficiency in the plant, the engineers may have to make adjustments to the programming logic, and those adjustments are stored in the RAM memory. Then that leads us into ladder logic. And ladder logic is pretty much the basis and the basic programming language that is utilized for programmable logic controllers. It is easy to use graphics interface type of language. So it's kind of like a drag and drop type of situation where there are actual, like for example, a relay. You don't have to actually have a specific string or word or code to depict a relay. There's an actual picture of the relay that can be kind of like pulled or dragged and dropped into the program for the PLC to read and understand that indeed it's now reading for a relay. So that's what is meant by graphics-based interface. The programming language resembles an electric schematic drawing. So in the code, you'll see actual depictions of a relay, depictions of a switch, depictions of a push button. And with that graphics-based interface, the user is able to determine and tell, okay, these are the types of inputs that are being used based off of the picture, not so much elaborate coding or words, but it's the actual picture that they're able to see and identify to know what's being input into the system, and then what the expected outputs are supposed to be. It is easy to troubleshoot the programming code in ladder logic because it's easy to see the logic flow from the left side over to the right side. And in the next slide, we have an example of ladder logic. Here we have a motor starter relay, and I'll go back. So again, this is a ladder logic example. We have a motor starter relay. And here we have the relay here where we have a start and then we have a stop. And then this is how it can be read from left to right. So this is the type of coding example that engineers would use in developing the coding language for a PLC. Next, we have the LQR, LQG design. It's a linear quadratic regulator and Gaussian design. And so the purpose of the LQR and LQG design is to help obtain optimal gains that yield more stable controlled responses in the design of a controller. And so the whole idea of a PLC, and especially in a closed loop system, is to have high stability. And in developing an LQR design, that's what our goal is. And in a lot of examples that one would see in studying the LQR and LQG would be like the inverted pendulum. You're able to see exactly how the design of that system is able to be stabilized with the implementation of these type of regulators and controllers. In the normal LQR regulator, the desired trajectory is a 0 state. So that's the ideal, but sometimes you don't always have a 0 state. And then that's where you would consider the LQG and the Gaussian to take into account any type of noise and disturbances. And so you would have a Kalman filter that would be used as a linear observer to estimate the system states. So the LQG, or the linear quadratic Gaussian, goes a step further to assess, what type of noises that and disturbances that may be going on with the system. And again, the whole idea is to have optimal stability, optimal control, so that the system, for the most part, can run by itself with minimal supervision, minimal interference by a person. The whole idea is, once the system is set up, for the engineers or skilled trade maintenance to just be on standby in case the line has to go down, whether for just routine maintenance, or if there is an emergency situation where something kind of does go out of whack and you might have a crash on the line, or where something stops and you want to keep production going, then the engineers will go in. But if you really have a strong design up front with the use of a linear quadratic regulator and Gaussian design, it gives you that optimal performance. So again, the idea is just to have someone on standby to just monitor from periodically, but not like full time, in terms of having to be hands-on and helping the system run when it was ideally supposed to be designed to run optimally by itself. And then in the next slide, we have some schematics and depictions of how the logic of the LQR and LQG is designed for the PLCs. So first, we have on the left-hand side the PLC start button. So we have here to start the system, that button would be pushed, and then we would go down. The next decision, the motor running at full speed. If we say yes, we would go down to say where the DC motor would stop running, or we would go back up here. If the decision is no, you would push the start button again. Again, if it's yes, you would have the DC motor stop running. Then DC motor delay for 10 seconds. And then down here, we would have DC motor start running with a 50% decrease. Or do we want to go back up to DC motor stops running? So again, these are the thought processes and designs in the background when defining the linear quadratic regulators. And then we have a depiction of the use of the Kalman filter for the Gaussian design. So there are advantages and disadvantages for programmable logic controllers overall. There first are plenty of advantages for these PLCs. And some of those advantages are a very fast scan time, a great computational capabilities, they're easily programmed and highly reliable. And again, this is with closed loop systems in mind. There are very few disadvantages. And some of those disadvantages would be the length of the downtime can be uncertain, and it can be depending on what issue might be present. So if it's routine maintenance, usually the skilled trade, they have in mind an idea of how long a particular line or equipment cell may be down for, and they can usually go in, do what they need to do, and come back out within a reasonable amount of time for that line to get up running again. But if there's some deeper issue or prolonged problem, then that the length of downtime, it can be uncertain. And then the limitations of working under high temperatures and high vibration node conditions. So in particular in auto factories, for instance, in the summertime, it can get very hot. So a lot of plants now have AC, to keep the working conditions cool. And again, that central air can also be programmed and operated off of the same programmable logic controller to help keep things regulated all the way around inside of a facility. And then vibrational conditions, depending on the location of a facility, if it's prone to earthquakes or other unforeseen disturbances with vehicles or other events going on that might cause some sort of vibrational issue or condition, the PLC may have some issues. But again, if that's a regular occurrence in the area, then maybe the PLC would be able to take those types of conditions into account as well. But then again, you never know if something is unforeseen, then the downtime will be longer, and then it creates limitations for the PLC. So here, I just have a few references that I wanted to acknowledge that I went to for research. I have the library.automationdirect.com, also the Polytechnic Hub, instrumentationblog.com, ACC Automation, and Ladder Logic World. Those are a few of the places I went to for additional reference when studying and researching PLCs. And then lastly, I just wanted to give an example of the many manufacturers for PLCs. These are some of the main ones that you may see when working in a manufacturing environment. I previously worked for an auto manufacturer, and the main PLC manufacturer and provider that I worked with was Allen Bradley and ABB. And so these are the types that you will see a lot when working in a plant or a factory environment. These are pretty popular, and they have high reliability and a great reputation in the manufacturing industry. So this concludes my presentation on programmable logic controllers. I thank you so much for your time and interest in this project. And thank you to Professor Farouk for his guidance in my studies and research. And the University of Michigan Dearborn. I'm very thankful and appreciative for the guidance that I've received. And again, my name is Michelle Larsosa, and I just thank you for your time.